Hello, students. In the series of learning computer organization and design, today we will discuss about the basic computer organization. And in that particular chapter, we are going to explore about the common bus system in terms of the basic computer configuration and the various types of instructions that can be used in the basic computer. So let's understand the agenda of today's lecture again. So here is the agenda. As I have already discussed with you, we have already discussed the instruction codes and the computer registers. Now we are aware that in a basic computer, the configuration that we are taking is it is 4096 into 16. So 4096 is nothing but the size of memory or the RAM of this particular basic computer. Along with that, this 16 bits, these are the number of bits which are depicting the size of each word which is stored in the memory. Okay. So the idea is that this 4096 configuration, as we were discussing in the previous chapter, that why we have taken this configuration only, because we have to make you aware of a simple computer's internal hardware organization. So in order to learn that, we have considered a very specific configuration. So basic computer usually deals with the processor and the RAM. So these are the two things which are most important components of any of the computer. So that's why we are working on this configuration, and on the basis of this configuration we have understood that what are the instruction codes and what is the size of instruction that we are going to use in this basic computer. Along with that, we have also learned various kinds of the computer registers that we can use under this basic configuration. Now, today's focus is entirely on the bus system. The basic idea of the bus system is explained in detailed manner in the previous chapter of register transfer and micro operations. So, I would like you, if you haven't gone through this particular topic in detail, so first of all, go there because today I am eliminating the basics of bus system, like how we can design it. We will directly work on the design part of the bus system based upon the types of computer registers that are associated with the basic computer. So after this, we will also discuss various types of instructions existing with this configuration of 4096 cross 16. So let's start understanding this. So first of all is the basic computer. So the common bus system of a basic computer. So guys, it is very important to understand here that the common bus system that we are going to learn here is purely in regard to the basic computer configuration. So my point here is that if we are using a different configuration, like for a modern machines, the configuration will vary. So according to that configuration, the number of resistors we are using in these modern machines will vary. So according to this, the common bus system that we will be designing or the constructing, that construction may also vary. Okay, so today we are going to learn only in context of this configuration. So the next thing is that this gives us savings in circuitry over the complete connections between the resistors. So what exactly we are going to learn from this bus system is that how each and every resistor which is associated with this basic computer is connected together through the bus system, and the bus system is basically being designed here along with the use of the multiplexer. So before starting learning about the bus system design, let's again understand about the different types of the resistors which are being used in the basic computer. So the point is basic computer registers. So let's understand those. Just recall those. You might have understood it in detail in the previous sessions. So I think we are using one register. We called it as the instruction register, which holds the data of the instruction. We know that it is a 16-bit. Reason being the size of instruction as mentioned here is of 16 bits. Similarly, there is a data register that we will use. Again, this data will consist of the data which is stored in the memory. Now, whatsoever the data is stored in the memory, so we know that the size of this memory is 16 bits only. So definitely this data register is also of 16 bit. I have explained in detailed manner about the size of these registers and their functionalities in the previous recorded session. Okay, so you can refer that also. Similarly, there is a temporary register. Again, if I have to hold the data in between any particular instruction, then definitely the data is of 16 bits, so the temporary register would also be of the same bit. Then there are input resistors. There is an output resistor. Now the size of this resistor, along with the configuration of basic computer, so it is only of 8 bits. So you can easily remember that, right? Similarly, along with that, we are using the program counter and the address registers. Now, address registers, we know it holds the address of the instruction. Yesterday, I taught that this 4096 can be considered like 2 raised to power 12. It means 12 combination of bits are required, starting from 00000 means which are the 12 bits till 1111, so on up to this, up to the size of 12 bits. This will depict the size from 0 to 4095. So definitely this is nothing but the address. So this address will be holded within the instruction register. Okay, so it is of the 12 bits. Along with that, there is a PC. We call this register as a program counter also. So usually the functionality of this program counter is to hold the address of the next instruction. So as soon as, let's suppose, this particular first instruction is working, so the next instruction, let's suppose, is the one right below it, right? So program counter will always store the address of the next instruction. So that's why it is again holding the address. So the size of this instruction, this register, is also of 12 bits. So let's understand in more detail that how these all registers, I can connect them through a common bus system, which has been designed with the use of the multiplexer. So that's it. So this is what we are going to learn. So this entirely is the block diagram of a common bus system, which has been constructed in a manner that the construction is based on the multiplexers, right? And it is using all the resistors which are being used in the basic computer. So let's start understanding them. Now, if we are using the multiplexer, so definitely we have to control the data also. So for that, we need a function table. So these are S0, S1, and S2 bits, which are controlling here. Okay, these are nothing but the control lines, which will control that which particular resistor has the ability to transfer its data on the common bus. So let's understand that. But before that, I would like to show you the function table. So this is exactly the function table. As I said you earlier, also there are number of resistors. These number of resistors we are using within the common bus system. So the idea here is that I can provide any control line to any of the resistor. So need not to cram anything. So I can provide the things. Now the thing that I need to remember here is this is 0, this is 1, this is 2, 3, 4, 5, 6, and 7th line of the multiplexer. This will help me to place the data, exact data on the bus line, and to transfer the data from the source resistor to the destination resistor. The other point that you can easily determine from here is that the data is moving from either of the source resistor. Now, any of this resistor, which is part of the common bus system, can be the source resistor. So this side, this entire size, will be consisting of the source resistors. Okay, and this entire size, the line here or the side, is nothing but the destination resistor. So this is important to understand. Now let's understand how this entire circuit has been designed. So again, this common bus system is nothing but it is only representing the block diagram. So we are not representing in detailed manner about how this entire thing is happening. Okay. So for the time being, it is only representing the block diagrams. That's why it has been mentioned in this way. So this is bus and this is nothing but the common line. Okay, it will remain the same. This is also the same. See, this is a pipeline for transferring the data from the source register, and through here it will be transferred to this side. This is again nothing but that common line, which will help me to transfer the data to the required destination register. So again, what I did is I have arranged the address register, program counter, data register, accumulator, input, instruction register, temporary register, output register on the line. So then along with that, I have also attached the memory unit into it, because whenever there will be an address register, so address register need to refer to the memory address always. So that's why we need sometimes to refer to the memory directly. Same is for the program counter also. We need to refer to the address register and the address of the instruction. That's why we are having that. Okay, so let me again delete it, make it neat and clean so that you could understand each and every point in detail. So this is the memory unit. So if you can look here, I have mentioned here some numbers: 2, 3, 4, 5, 6, 7. These are nothing but these bits, selection line bits. Okay, like this. It is 0. 0 means no register has been selected. So selection line 00 is not going to help me to depict any result. Similarly, AR is for standing for the first line, second, third, fourth, and like memory was there, ahead memory, 7 is been written. So that's why 7 is representing that. If the selection line is 111, I will select the seventh pin of the multiplexer, and the seventh pin is nothing but holding the memory. Got it? So let's understand in more detail here. So this 7 is representing the memory. This is the first line pin of the multiplexer, which will take the data from the address register on the common bus system, and ultimately whomsoever it want to transfer the data will be responsible for getting the data. Now within the memory, two operations can be done: read and write. That's why this read and write is operation has been performed here. Similarly, in the address, program counter, and all the other registers, what we are having is one is the load bit. This load bit is very significant here. Okay, the reason is that the load bit, the one who is able to receive the data, the destination register, should have the load bit equals to 1 in order to receive the data. This is the point. I will show you in the later part of the sections that how this load bit is also dependent on this. So for the time being, as we are only working on the block diagram, so I will just provide you in a layman language that who is going to take the data as a destination register. So the one who has the load bit equals to 1. Let's suppose I have in this particular selection line, the address register has been selected. Okay, so if address register is selected, so it want to transfer its data to the program counter, let's suppose. So how it will done? So the selection lines would be 001. So it will simply take the data from the address register. This value will be selected. Okay, so address register will hold its data on the common bus system, and ultimately if this program counter has to receive the data, its load bit should be equals to 1. Then the program counter will be able to receive the data. Once this load bit will be equals to 1, rest load bits would be equals to 0. Some logic has been used here. Again, I am saying it is only the block diagram. For the time being, you have to understand it in this way only. Similarly, we have also applied ALU here. ALU is nothing but the arithmetic logic unit. Okay, so all the arithmetic operations should have to be performed here. Now the arithmetic unit is taking the data from either the data register, definitely. So if I have to perform anything on the data will be present in the data register only. Similarly, the data that we are representing here in the arithmetic unit should also be taken from the accumulator. Now accumulator, we know that accumulator is also known as the processor register or the general purpose register. Remember in the previous topic I have explained you this. So why we called it so? Because it has the ability to load and to store the data. Okay, so that's why. So that's why I am able to store the data here. That stored data will be used in this accumulator, and whatever the value I will get will again get stored here in this accumulator. Okay, so this E is there. E is representing the overflow, means sometimes in the addition, let's suppose I am adding the numbers like 101 and 101. So what I will get, 1 plus 1 is 0 and 1 as a carry. So 1 plus 1 is 0 and 1 as a carry. So we know that the destination register should also be of 3 bits. So where to store this particular value, so this will go in this E overflow buffer, so will be stored here for you to be used in the future instructions. Okay, so along with that I forgot to tell you about these two lines also. These are the increment, this is the increment control line and this is the clear line. So within any of the resistor I might have to increment the value of resistor by 1 at any point of time. Okay, like usually it happens in the case of program counter, I have to increment the value. Okay, similarly I can have to clear the value also to 0000 due to any particular reason when I am resetting the buses or something like that. So accordingly this value of AR can also be cleared. So these are the three control lines attached to each and every resistor which is part of this common bus system. Now, along with that, there are input and output resistor. You might have observed that these resistors are actually not directly participating in this common bus line. Reason being, these input and output resistors are basically connected with the peripherals. Okay, like input devices and output devices. So the idea is that these input and output devices are responsible to take the instructions from here, and they cannot directly talk to the memory. They don't have this privilege. They don't have direct access to the memory. That is why they can, if any of the input is been coming here in the input register, it can directly be stored in this ALU. Similarly, whatsoever the data we want to get, okay, we can get it here. And all these resistors are connected together through the common clock pulse, because once this common bus system will be activated, these all resistors have to remain active. That's why. So only but the one who's having the load bit is equals to 0 and whose value is present in the selection line, only those will be participating in the transferring of the data. So this is all about the common bus system. If you have any doubt in case of this common bus system, you can ask me. Otherwise, let's proceed with the next topic. So you can also read these points for your clarification. Like as I've already explained you from the diagram itself, either one of the resistor will have its load signal activated, right? As I said, the only one resistor will have load is equals to Z, or the memory will have its load read signal activated. So the read signal of the memory one is equals to this will be able to receive the data. Okay, this will allow the resistor to read the data from itself. So then the 12-bit resistors, I told you that why these are 12-bit resistors, address and the program counter, same why these are of the input and output are why these are of 8-bit resistors. So let's proceed ahead. The next topic, which is the basic computer instructions. So before starting this concept of basic computer instructions, let me revise you about the instruction format of a basic computer. Remember, the instruction of the basic computer is actually of 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, Need to delete. I just want to demonstrate you in a better way. That's why I am trying to provide all these 16 pins here. 13, 14, and 15, right? So what my point here is, this is the instruction format. The instruction is of size. The instruction is of size 16 bits, right? So that's why I have represented these 16 bits. We know that in the register transfer language, RTL, we have taught you guys that the least significant bit will be present on this side, means the right hand side, and the most significant bit will be represented here in this left hand side. So this 0 till 60, 15 are representing that the size of this instruction register will be 16 bits. Now the next point is, this instruction register or the instruction format is actually being divided into three parts. One part, which is 0 to 12, 11, right? So this is holding the address of memory. Then 12, 13, 14, 3 bits are there, which are representing the opcode bits. Means what to do, which kind of micro operation I want to perform. And this is the 15th bit. It is also called as the mode bit, right? So it will simply depict that under which mode my instruction will work, how to determine the exact data from the address given. So if it is 0, it is a direct indirect mode. If it is a 1, it is indirect addressing mode. So this is representing nothing but the addressing mode, how to figure out the exact address of the instruction. So basic computer instruction, depending upon its configuration, is having these three important components, and each and every component I explained you here. Now my point here is that we are learning that what are the different types of computer instructions under the category of basic computer. So broadly, there are three types of instructions. There are some instructions which we call them as memory reference. Means for any kind of data that they are looking for, they always refer to the memory, right? Then there are some instructions who don't need to refer to the memory for computing the results or for figuring out any of the data. They will simply refer to the registers only for getting the data. Then there is a third type, we call them as input output instructions. Remember, in the common bus system, I was saying input and output register need not to be connected to the bus line because they will take the data from the hardware equipments or the peripheral devices, right? So that's why such kind of instructions fall under the category of input output instructions. Now how I can distinguish that any instruction is memory reference, anyone is the register reference, or the input output reference. So let's understand them. So if any instruction is the memory reference instruction, okay, so the idea is that it will have a 12 bits address, right? Any 12 bits address, any kind of address, any combination of 12 bits, some opcode bits will present, and this value I see, this opcode bits I need to remind you here. This is 12, 11, 12, 13 and 14. So 12, 13 and 14 bits are there. What could be the combination of it? These are 3. So maximum from 2 raised to power 3, I can generate the 8 results like 0, 0, 0, 0, 1, 0, 0, sorry, 0, 0, 1, 0, 1, 0, 0, 1, 1. Similarly, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So in this, in order to determine that any instruction is falling under the category of memory reference, then these opcode bits will lie from 0 to 6, like 2, 3, 4, 5, and 6. And this seventh will not be part. Means at any point of time, this value should be the combination of bits should any be from this 0 to 6, but it should never be in this 1, 1, 1. Otherwise, This value of mode bit could also be 0 or 1. This address bit could also be of any kind of address bit, any combination of 12 bits. But this value of opcode should lie from 000 to only 110. So this is the only point to understand. In case of memory reference instruction, then such kind of instructions will be referred by the computer as the memory reference instruction. So how my system will determine that any instruction is a register reference? So again, what we are left with? We are left with only this 111, right? So any combination of the 12 bits will be present here. Okay. Then along with that, this 12, 13 and 14 bits, these would always be 111, and the value of this I bit should always be 0. The mode bit should always be 0. The opcode bits should always be 111, and any combination of these 12 bits will determine that this particular instruction is falling under the category of register reference instructions. Okay, same is the case for this input output reference instructions. So any combination of 12 bits, along with that this 12, 13 and 14 bits being 111 always, and this mode bit, this I bit should always be equals to 1, and the opcode bit should always be equals to 111, and the any combination of 12 bits will determine that this instruction is falling under the category of input output instructions. So this is how we can determine, or my system can determine that any particular instruction belongs to which category. So broadly three categories: memory, register reference and input output reference. Again I am repeating, for memory reference I need the value of opcode bits to lie from 000 to 110, and the mode bit can be any bit, either 0 or 1. Same for register reference, the opcode bit should always be in 111 and the mode bit should always be 0. Similarly for input output reference, the mode bit should always be equals to 1 and opcode should always be equals to 111. So this is the detail of the different kind of instructions which are available in the basic computer. So this add and all these are basically referred to as the memory reference instructions. These are the register reference instructions, and these are nothing but the input output reference instructions. We will learn in detail about these in the later part of the sections. So after this, if I have to tell you that there is another categorization also, like I can say that any instruction can be of type functional, means it is performing something like arithmetic or logical or shift instructions. Kind of instructions can come under the category of the functional instructions. Similarly, certain instructions are there which are responsible for transferring the data. Okay, so from one register to another register, like load and store. So these kind of instructions are called as the transfer instructions. So some instructions are controlling the data also. So this like branch unconditional, branch and save return address, and ISGs increment and skip if it is 0. So these are called as the control instructions within the basic computer. Input output instructions are there, which are referring to any providing any input and providing any output. Now all these things which I am denoting here, add, CMA, ICNC, LDA, these are nothing but the RTL notations of the instructions. We will learn in detail about these RTL notations and different types of the memory reference, register reference, input output reference instructions in the later part of the sessions, or you could say upcoming sessions. So stay tuned till here. So with this, I'm about to end this session. I hope that you have understood the idea of common bus system and the various categorizations of the instructions within the common bus system. Thank you so much for watching.